Good evening, Professor.
Good evening, sir. Good evening, Dr. Lovarathan.
Good evening.
Satish.
Yeah, good evening, Professor. Good evening. Professor Banu also there in the group.
Yes, Madam also joined.
Also joined. Okay.
Sir, whether all the 9 candidates reported?
I hope so, Professor.
Good evening, sir. Good evening, dear professors.
Good evening, madam.
Yeah.
Good evening.
Yeah, actually, not all of them are present today,
Good
sir.
evening to all.
Actually, the last person, that is Dr. Rohan Mishra, he has informed that he won't be able to join.
Okay. Last person.
Everyone else, it will be there.
Okay.
Okay. Except the last one. Okay.
Yeah, except the last one. He was saying something regarding the timing because it's very early for him, so he's in the US.
Oh, okay.
No, not that. No, 1 second. I'll just confirm. He said some reason. 1 second, sir. Yeah, it's not that. He didn't respond. That is it. It was Dibjoy Thakur who said about the timing. Actually, Dr. Rohan Mishra, he didn't respond to our mails and WhatsApp messages.
But in USA, it will be morning 8 a.m. So there is
no. He's not in the US, sir. It was yesterday's participant, Dr. Dibjoy Thakur, who said he won't be able to join because of the timing. Dr. Rohan Mishra actually didn't respond to our mails and WhatsApp messages. I tried to call him also. He didn't pick the phone. That was what happened. He's from Greater Noida, Delhi.
Okay. Okay, I think before 5:27, isn't it?
If you permit, you can call one first candidate because it takes time in loading paper, etc.
Sure, person.
Okay, so
We can
shall
check
we
whether.
initiate?
Yeah. You can let us start.
Okay. So good evening once again, dear professors and all the participants. We have entered the second day of the final evaluation for Best Paper Awards in association with ICSTC 2024. We have our respected jury members, Professor Loganathan, who is the jury convener, Professor K.S. Bhanu, and Dr.
Good evening to everyone, sir.
Good evening, madam.
Yeah.
Good evening to all.
Good evening. Good evening.
Good
So
evening, Dr.
we. Good evening, professors. So we, on behalf of the organizers of ICSTC, we extend a hearty welcome to all dear jury members once again. So over to you, Lognathan sir. Let us start today's proceedings.
Good evening to all. Good evening, Professor Ghosh, Professor Banu, and Professor Satish Kumar, Dr. Subha. Let us see whether all the competitors are present. First, Jiju Gilarios. No. Next one, Abhishek Singh.
Yes,
Hello?
sir. I'm present.
Abhishek Singh. Oh,
Yes,
you
sir,
are
yes, sir.
available. Dr. Satyanarayana.
Present, sir.
Here. Dr. Haripriya.
Yes, sir.
Dr. Remyanath.
Present, sir.
Right. Dr. Sarath Sindhu Mukhopadhyay.
Present, sir, so not doctor.
Dr. Rahul Banerjee. Dr. Divya Denis.
Present, sir.
Well, madam. So, okay, right. So, Dr. Jiju Hilarios, not available. Sir, the first candidate has not joined so far. Professor Ghosh, Professor Banu, shall we
Yes,
call
sir.
the candidate Dr. Abhishek Singh for
Yes, sir.
the
Yes, sir.
presentation?
That candidate will be given last chance. Huh? You call the second
Yes.
candidate.
Right. Dr. Abhishek Singh. Dr. Abhishek Singh. Hello.
He was there. He was there.
Yeah, he just
Yes,
before.
yes.
Is there?
Dr. Abhishek Singh.
Dr. Abhishek Singh, can you present your...
No. He doesn't appear now.
So yeah, some network issues probably he may have. So can go to that.
Dr. Satyanarayana.
Yeah, he's
Yes, sir.
Dr. Satyanarayana Pujari.
Yes, sir. Yes, sir.
No, Dr. Abhishek Singh's joined, it seems. Dr. Abhishek Singh.
Yeah, he is joined.
Hello.
yeah. Now he's there. Yeah.
Yes, sir.
But
Yes, sir.
can
I'm
you
audible, sir?
please? Yes, you present. Share your screen and start presentation.
Okay.
And as organizers yesterday mentioned, 15 minutes for presentation. Accordingly, you manage your slides. And there shall be 5 minutes for discussion. Dr. Abhishek Singh, share your screen.
Yes, sir. Good evening, everyone. Myself, Dr. Abhishek Singh, working as Assistant Professor, Department of Mathematics and Statistics, Dr. Vishwanath Krap, MIT Wadapis University. I am going to present a paper titled Nucleoscopic Regression Sampling Method and Estimator for the Estimation of Population Mean. These are the contents. Before introducing nucleoscopic regression sampling method, I want to introduce what is regression sampling method. It was first proposed by McIntyre 1952. It is less time consuming, cost effective, and most of all better suited to simple random sampling. Initially, it was investigated for ecological and environmental survey, but nowadays it is applicable in every field, various fields, where the exact measurement of the selected sample either difficult or expensive in terms of time, money, or labor. But ranking of small sets of sample on visual basis or some other method can be done easily. Suppose we want to estimate the mean height of the trees in the dense forest. So height of the tree could pose a problem, but ranking up small sets of trees can be done on visual inspection methods. If ranking is not possible with the height, the ranking can be done with its width or diameter or volume. That is another variable highly correlated to the study variable is known as auxiliary variable. We have, suppose we want to estimate the mean height of 80 population. We have 80 population like this. The range sampling procedure followed by this. We select M set of sample each of size M, rank them which is within each set. Then we select the first small unit from first set of sample and discard the rest of the units and count it for the first measurement. Similarly, we select the second smallest unit from the second set of sample and discard the rest of M-1 units. And so on, proceeding up to the M term. So we select the largest unit from the last set of sample and discard the rest of units. So we have total M research units from the actual measurement out of M square units. If this process repeated n is equal to r times, so we have total n is equal to mr unit for the actual measurement out of m square r units. A visual illustration can be seen from here. We have 3 sets of sample, each of size 3. And after ranking, we have units observation are like this. We have selected first smallest unit from the first set of sample, discarded the rest of 2 units. We have selected second smallest unit from the second set of sample, discarded the rest of 2. And we have selected largest unit from the last set of samples, discarded the rest of units. So out of total 9, that is m square units, we have 3 actual, that is m ranks sample for the actual measurement are placed in diagonal. Population mean is given by question 1.2. Ranks sample mean is given by question 1.2. Simple random sample mean is given by question 1.3. And from question 1.5, we can see that variance of ranks sample mean is given by equal to variance of simple random sample mean minus these positive quantities. It clearly states that ranks sample is better substitute of simple random sample. Now come to the topic nodestopic statistics. The concept of nodestopic was explained by Florentine, Smart, and Deche, which is generalization of both classical as well as fuzzy statistics. Many experimental machine pass data are in interval type due to measurement errors. Some water level data, blood pressure data, daily temperature data, multi-point data, and such type data are lies in interval. In fact, real-life scenario interval type data exists more than the crash type data, and classical method will be risky, time-consuming, or laborious or costly to deal such type data. So the classical statistical methods are the techniques are method failed where nodestopic data are present and nodestopic statistics replaces classical statistics. The classical ransom sampling method will cause some loss of information for such type data. So nodestopic ransom sampling method for such type data will be based on most reliable estimate for the estimation of population parameters. Nodestopic ransom sampling procedure. We generally representing nodestopic number by this expression, where I denote the indeterminacy in the data and represent the nodestopic number. Nodestopic number are represented by interval type. A and B are the lower and upper value of the nodestopic data. Ranking of nodestopic sets and numbers. Suppose we have 2 sets, x1 and x2, and their midpoints are x1 and x2. X1 mid and x2 mid. The nodestopic number x1 will be less than 2x2 if x1 mid is less than x2. The nodestopic number x1 will be less than x2 if x1 mid is equal to x2 mid, but x1 lower is less than 2x2. If x1 lower is equal to x2 lower and x1 upper is equal to x2 upper, then x1 nodestopic number will be equal to x2 equivalent to x2 nodestopic number. Nodestopic ransom sampling methods. The nodestopic ransom sampling method consists of drawing m bivariate nodestopic ransom sample for each of size m from the population n, ranking them which is 8 set within each set. Concerning to the auxiliary variable associated with the study variable. Ranking the auxiliary variable are perfect, where in study variable there are some error. Then by procedure, we take the smallest unit from the first set of sample and count it for the first measurement and discard the rest of unit. Similarly, we take the second smallest unit from the second set of sample and count it for the second unit, discard the rest of unit. Proceeding this way up to the m terms, we have total m nodestopic bivariate observation from the m square units. If this process repeat r times, so we have total n is equal to mr nodestopic bivariate observation, ranks observation from the m square r population. For example, if 5 sets are taken each of size 5 and replicated 5 times, and for first cycle the nodestopic bivariate ranks sample structure is given by like this, and we have selected first small unit from the first set of sample, discarded the rest of units. We have selected second smallest unit from the second set of sample, discarded the rest of unit, and proceeding this way we have selected largest unit from the last set of sample, discarded the rest of unit. So out of total 25 ranks units, we have 5 nodestopic ransom sample for the actual measurement are placed in diagonal. If this process repeated 5 times, so total we have 125 observation, and out of which 25 nodestopic ransom sample for the actual measurement. And population mean is given by equation 2.1, and nodestopic ransom sample mean is given by equation 2.2. Nodestopic simple random sample mean is given by equation 2.3, and also we can see from clearly equation 2.5 variance of nodestopic ransom sample mean equal to variance of nodestopic simple random sample minus these positive quantities. We can also see from here that nodestopic ransom sample is better substitute of simple random sample, as it provided less efficiency than to the simple random sampling. Ratio and product type estimator under nodestopic ransom sample. We have given under bias estimator by question 3.1, and its bias MSE or variance given by question 3.2. Some ratio type estimator are given by question 3.3 to 3.7. Some product type estimator are given by equation 3.3, 3.8 to 3.12. And we have also proposed some generalized a generalized class of estimator as given by question 3.3 is bias and MSI are given by question 3.34 to 3.35. It's optimized MSC given by question 3.3 and for different choices of A, B, delta. Delta, we have some ratio product type estimator in table 3.1. Like this. Since classical Renaissance sampling is better suited of simple random sampling to showing numerically that our Nootescopic Renaissance sampling is also better than Nootescopic simple random sampling, we have given a generalized class of estimator under Nootescopic simple random sampling is given by question 3.37 and its bias and MSE are given by question 3.38 to 3.39 and its optimized MSE given by question 3.40 like in table 3.1, table 3.22 was also obtained. Due to time bound, we are not shown here. An empirical study is conducted. Real data is study conducted on sweat temperature versus next day global horizontal irradiance, and the result we have we have done total and it's equal to 6 sample where set size is 3 and replication is 2 and population is I think 12. And its population is 12. And its result is given by in this table, we have shown MSE and relative efficiency of the proposed estimator over unbiased estimator. We can see from the table that relative efficiency of the proposed generalized estimator is the highest than to the other estimator. And this means that generalized estimator has performed better than to the other proposed estimators. We have also given comparison of Nootescopic estimator over Nootescopic simple random sampling estimators, and we can see that all the relative efficiency are greater than 1. This shows that Nootescopic sampling is better than to the Nootescopic simple random samplings. We have also conducted simulation studies on the artificial data. Data is generated for multivariate normal distribution, and we can see result here. This table shows the MSE relative efficiency of the proposed estimator and the over unbiased estimator, and taken for the correlation coefficient 0.75 and -0.75. We can see that also in this table, the relative efficiency of the generalized class of estimator is highest than to the other proposed estimators for the both correlation coefficient. This shows that our proposed generalized estimator have performed better than to the other estimators. So we have also given for that on the artificial data a comparison of Nootescopic Renaissance sampling estimators over Nootescopic simple random sampling, and we can see all the relative efficiency are greater than 1. This shows that Nootescopic Renaissance estimator are performing better than to Nootescopic simple random sampling estimators. Further, we have also taken same evaluation for the correlation coefficient 0.95 and -0.95. We can see that also our proposed estimator have performed better than to the other proposed estimator because it had highest relative efficiencies. We can also show that on increasing the correlation coefficient, our relative efficiency also increasing, like in the Rankin sampling methods. We can see that here 1.86 to 2.26, and here for the same sample size and for the correlation coefficient 0.95, we can see that it is coming out at 3.2 to 11.02. This means our increasing correlation coefficient, our relative efficiency also increasing, sir. And same relative efficiency, same comparison of Nootescopic versus simple random sampling. And here again we have shown that Nootescopic Renaissance estimator are performing better than to Nootescopic simple random sampling estimators. And we have also given a comparison of Nootescopic versus classical. This is the Nootescopic result, this is the classical results. And we can see that our generalized estimator have performed better, and we observe that even classical Renaissance sampling values is less than to lower value of the Nootescopic result. Means even Nootescopic values, lower value is performing better than to the classical results. Means we are here causing some loss of information. Means we are ignoring some loss of information. We are getting some unfair results means done to the
Abhishek
unfair
Singh,
result
you
done
have
to the
2 minutes.
Okay,
You have
sir.
2 minutes.
About to finish, sir. We have given notes of the ransom sampling method. Further, we have derived based on product type estimator and the have proposed generalized estimator. Our proposed estimator have shown supremacy over Rossi and product test estimator. The sensitivity analysis of the proposed estimator is using any analysis is the same as classical ransom sampling. Like classical ransom sampling, better substitute of simple random sampling. We have shown that noticeable ransom sampling method is also better than to noticeable simple random sampling. Our noticeable ransom sampling is efficient and reliable method than classical ransom sampling method for noticeable data. Future study various noticeable ransom sampling method can be further defined like in classical ransom sampling, like median ransom sampling, extreme ransom sampling, double ransom sampling, percentile ransom sampling, and so on. By changing estimator or estimation method, further study can be done. That is, generalized estimator can be replaced with family of exponential type estimator, or other sampling methods can be other ransom sampling method can be replaced. Not even sampling theory, but other field of statistics such as like in providing control chart, inference, reliability, non-parametric estimation, testing of hypothesis. Further noticeable ransom sampling method can be used. We have solar energy data that is useful in energy injustice. In the production of machinery parts, components, production of manufacturing of different kind of products, the data lies in trouble due to the measurement error. For such type data, in providing statistical quality control and acceptance sampling process, a noticeable ransom sampling can be used. In testing the reliability of drugs whose effects often are certain and determined, the noticeable technique will provide best and most reliable than to the ransom sampling methods. In crop yield production, measuring soil quality, water quality, in air pollution, it is such in providing quality statistical quality control and a certain sampling plan. Any research can be used. This method is also useful in agriculture and environmental industry too. Thank you, sir.
Well, congratulations for keeping in on time. Now the question starts. Dr. Banu, do you have any questions?
Hello, Dr. Abhishek.
Yes, ma'am.
I have two questions. First is, what is the motivation for taking up this study? And the second is, what is the basis on which you rank the variables? Ranking is...
Suppose we want to estimate the mean height of trees in the dense forest, ma'am. But if you would take a simple random sample of size 3, then there could be a three random sample of small sizes, medium sizes, or tall sizes, or mix of sizes. But we take the ransom sample method, then we always get the one size of small, one size of medium, and one size of tall. So this is the method. This is the reason to studying the ransom sampling method, and why we are doing under noticeable statistics, because in day-wise temperature we notice that temperature always day-wise temperature always lies in minimum and maximum, and someone is estimating the monthly average temperature is something crisp value, providing the 35 degree. That is not fair. It will be fair when it is provided. It is light monthly average temperature lies in 25 to some 32, 31 as someone provided. Then it will be reliable estimate than to the crisp type result.
So in that case, you use that.
Yes, ma'am.
And you mentioned some applications in the last slide.
Yes, ma'am.
So are you likely to carry out those studies, or it is a general statement that you have made?
I have given a direction to some other field to researchers. I am also planning to do in the same field, ma'am.
Which field?
I am also planning to do research on that field in the correlation of the part of that field.
No, there are 4 or 5 applications you have listed: environment, manufacturing, industry. So
yes,
you
ma'am.
may not be able to take up studies in all the fields, no?
Yes, ma'am, but I have given a direction to the researcher who are as part of that field.
I see.
Professor,
Okay.
Professor Ghosh? Professor Ghosh?
Yeah. Dr. Abhishek, can you come to the definition slide of definition of ring sampling?
Yes, sir. This one, sir. Yes, sir.
Next. Yes, sir. Now, my question is this. So, you have taken 3 units.
Yes, sir.
And whose rank is the lowest you have selected first?
Yes, sir.
then again you are taking in same 3 units.
No, sir. It's a different sample, sir.
Different samples.
Yes, sir. Different sample, sir. Yes, sir.
So, again you are coming small. Now my question is that you have the 9 sample. Suppose it
Yes,
is a total population value. So 9 sample you have, and you have the total population. What is need of selecting 3 units by ranking? You have the rank 1, 2, 3, 9, and who have the lowest, then that 3 you select 3 units. What is need of all these sampling techniques here in rank sampling? I can just understand you have taken 9 samples, and 9
Yes, sir.
samples, you suppose it is total population, so find out whose total population is either maximum or minimum as a first rank, and first 2, 3 either from the top or from the 3 selected. 3 units are selected. What is
Yes,
need
sir.
of doing all this sampling?
Sir, taking different samples provide a better estimation than today. We can get the actually sampling purpose. It should be representative of the whole population. That is why we are taking different sample. We can get the actual. It will come out to be the representative to the population.
Simple random sampling also you are taking whole population. Simple random
yes, sir.
sampling. If I would take the 9 samples,
that is not.
It represents all populations. Nah?
Yes, sir.
What is benefit of this?
Sir, I have earlier explained that if you are taking simple and sample of 3 sizes, there might be a 3 small. There might be a sample of 3 small size.
Because the same example I have seen with Dr. Neha Garg's paper, the same example I have seen. That's why the question arises in my mind. I was referee for that paper. Same
Okay,
example, just same thing, same 393. Nothing
Yes,
different was there.
Yes, sir.
Well,
I asked the same question to her also,
Yes, sir.
but there was no response properly.
well,
No,
Dr.
sir.
Abhishek Singh,
Yes,
I have
yes,
one
sir.
question. That you have done some differentiation for nutrosophic distributions, right?
Yes, sir.
And yeah, I have. Do you have any references for calculus for nutrosophic sets of
No,
situations?
sir. I have cited some differentiation done in nutrosophic statistics paper.
No,
Taken
sir.
that
The thing
difference.
is, we have a very good calculus,
Yes,
and
sir.
we have a real analysis for verifying differentiability of a function.
Yes,
And
sir.
like that, is there anything regarding calculus for nutrosophic situations?
Yes, sir. Some are paper published on that too, but I have not cited that because my studies statistics. So
No, sir. The thing is, you have done something selection numerically, that is quite all right. But for as far as differentiations are concerned, there is no hardcore mathematics so far established for nutrosophic
Actually, sir,
situations.
he has defined out the Weiss or mean square error. Nah? So where is the calculus required here?
Well, thank you, Dr. Abhishek Singh. Close your screen.
actually, sir, we have taken the statistics representation, not
Okay, right.
mathematical representation.
Sorry, Dr. Satyanarayana,
Yes, sir. Yes, sir.
please. Dr. Abhishek Singh, you can close your screen. Satyanarayana, please share your screen.
Sir, whether my slides are visible?
Yes, visible.
Okay. Thank you, sir. Good evening,
Yes,
all.
visible.
Okay. Good evening, all. Myself, Satyanarayan. I'm going to present my research work on empirical likelihood, adjusted empirical likelihood, and Jacquemin's empirical likelihood version of modified Leibniz test. So these are the content I'm going to cover. So let me start with the introduction. So we know that in applied research, Leibniz test is the most commonly used test to assess the equality of variances among the k-independent normal distribution. In both one-way ANOVA as well as in regression scenario, this assumption is very much required. It was initially Bartlett in 1936 who has introduced conditional likelihood ratio test for assessing the equality of variances in k-independent normal distribution. Even though its performance is better, but it is highly sensitive to the normality assumption. Later in 1960, Levine has proposed a test for equality of variances in k normal distribution, and it was later improved by Brown and Proste in 1974, known as modified Leibniz test. Estimated type 1 error rate is smaller than the nominal level, and the test is more powerful compared to the Bartlett test. So the Leibniz test and its modified version is tend to be conservative, showing small type 1 error rate compared to the nominal level for small samples. On the other hand, when empirical likelihood ratio test introduced by Owen, a highly powerful non-parametric method can be used for testing the specified mean or equality across the several population. So these second line papers are related to the extension of empirical likelihood ratio test for the regression as well as the inference settings. In 2018 and 2019, we have worked 3 versions of empirical likelihood ratio test for Barian-Fisher problem. Recently, in 2024, we have proposed an empirical likelihood ratio test for testing the equality of, testing the presence of autocorrelation in the linear regression model, where we have compared with the 5 tests and show that our proposed tests perform much better compared to the all other 5 tests under consideration. These are the few papers showing the extension of empirical likelihood ratio test. So now coming back to what is the motivation for this work, we have seen that many empirical likelihood version of tests are available. One of the better properties, distribution free in nature. And also, when you look at the performance, better performance in maintaining size as well as exhibiting the high power. So that we are proposing empirical likelihood, adjusted empirical likelihood, Jacqueminot empirical likelihood version of Leibniz test as well as the modified Leibniz test. Totally 6 tests has been proposed in this paper, a valuable non-parametric alternative for the variance equality. Here our main aim is to verify both asymptotic as well as the finite sample performance. And we also compare the proposed 6 tests with the Bartlett test, Leibniz test, modified Leibniz test, and the Lowe's exact test, both under normality and the non-normal models. And we also reported what should be the minimum sample size required to maintain the size for each distribution. So now coming back to the methodology. So this is the hypothesis of interest, equality of variance among the K groups. Zij is the absolute mean deviation taken from the each respective group mean. So in this context, we are defining the empirical likelihood, adjusted empirical and Jacqueminot empirical likelihood version of Leibniz test. It is equivalent to testing the empirical likelihood ratio test for means of Zij, because Zij is the transformed version of the Yij. So these are the few other tests we use to compare with our proposed test. So this is the test statistics of the proposed empirical likelihood ratio test as given by 1, maximizing the product Ni Pij subjected to this constraint. We have also proved a theorem under regularity condition. Asymptotic null distribution of empirical likelihood ratio test statistics follows chi-square with k minus 1 degrees of freedom. So this is the rough sketch of that proof. So the equation 2 representing the empirical likelihood ratio test statistics. Without loss of generality, we refer mean of Zij as mu. With the simplification, we can show that mu cap is equal to this one, which is represented as Z bar dot dot. So, and we know that summation I running from 1 to k Ni Zi dot bar minus Z bar dot dot square is nothing but the treatment sum of square. So in one way, in ANOVA context, due to the internal studentization, this treatment sum of square divided by sigma square follows chi-square with k minus 1 degrees of freedom. And as follow the procedure given by Owen in 1988 and Quinn and Lawless, if you constructed the Lagrange multiplier approach for constructing the likelihood, take the log likelihood and differentiate with respect to corresponding Pij and solve for the model, solve for the parameters, we end up with the summation I1 to k Ni Zi dot minus Z bar dot whole square divided by sigma square, which is already shown that it follows chi-square with k minus 1 degrees of freedom. So therefore, this is a proof of rough sketch of proof of theorem 1. Next question is why we need the adjusted empirical likelihood. So when the convex cell does not contain the true hypothesized values, so there occurs a problem of infeasible solution. Owen in 2001 has suggested that we need to reject the null hypothesis when there is an infeasible solution. If you do so, it will lead to increase the type 1 error rate. And it will also lead to the slow convergence rate. So as a solution, Chen et al. In 2008 has proposed an adjusted empirical likelihood approach. According to this approach, an artificial observation of very small order is appended to the data set so that we are computing the empirical likelihood ratio test statistic for the n plus 1th observation. So such a way that it will redefine the convex cell to ensure that it will contain the true parameter. In fact, one of the better properties that he has shown that even though inclusion of the additional observation, asymptotic null distribution of the adjusted empirical likelihood ratio test statistics remains same as the original one. So accordingly, we have constructed equation 5 for the adjusted empirical likelihood ratio test statistics subjected to this constraint. Constraint are redefined with respect to n+1th observation. So next obvious question is what observation you will take as the n+1th observation, which is of the small order. So it is considered as minus an into zi dot bar, where an is the positive quantity. Chen et al. Only has suggested that better choice for the an is 1/2 log n. So with the help of this, we have the theorem to that under regularity condition, asymptotic null distribution of adjusted empirical likelihood is same as the ordinary empirical likelihood ratio test statistic. That is chi-square with k-1 degrees of freedom. Now coming to the Jacqueminck empirical likelihood approach. In this approach, we combine the two, Jacqueminck with the empirical likelihood approach. The main idea of Jacqueminck empirical likelihood is to turn the statistics of interest into sample mean based on the Jacqueminck pseudo observation. So once you are ready with the pseudo observation, the empirical likelihood can be applied. So equation 6 and 7 represent how we have constructed the Jacqueminck pseudo values with emitting one observation at a time. So we redefine the Jacqueminck empirical likelihood ratio test statistics given by 8 with the Jacqueminck pseudo values, and we have proved that under regularity condition, asymptotic null distribution of Jacqueminck empirical likelihood ratio test is also chi-square with k-1 degrees of freedom. Now coming back to study the finite sample performance with the simulation study. For the simulation experiment, we have considered the simulation setup as given by Ching et al. In 2016. For estimation of type 1 error rate, we fix the variance as 1. I'm showing the result for groups k equal to 3. We have also done it for k equal to 5, 7, and 10 also. Throughout the study, we fixed nominal level as 5% with the 3000 replication. To consider the various combination of sample size, so we have used the equation 9 as given by the Ching et al. So we can see that from the sample size starting from 4 to 50 with the different combination we are considered for 3 groups starting from 4, 4, 6 to 50, 50, 75. Along with the unequal sample, we are also considered some equal sample size combination. Next, to check the variances or the power, we have used equation 10 to generate the various combination of variances. You can see that in the epsilon starting from 0.1 to 2, which will cover small, moderate, as well as the large variances. Now let us come to the simulation result. Here we can see that size of various tests under the normal distribution. We can see that when the sample size is 16 and below, Bartlett test, Leibniz test, and the lower test maintain the size. But when the sample size is 20 or more, all the 6 version of empirical likelihood ratio test maintain the size. The same scenario we can also observe when you deal with the equal sample size. So this is the power of the various tests under normal distribution. You can see that this is the for sample size n equal to 12. The topmost one is the empirical likelihood ratio version of the modified Leibniz test. This is for the n equal to 24. This is for n equal to 28. The topmost one is the adjusted empirical likelihood version. This is for the equal sample size. After verifying with the normal distribution, then we'll check that whether the test is robustness when you deviate from the normality assumption. For that, we generate the observation from the gamma distribution. So this is the table representing the size of various tests under gamma distribution. We can see that when the sample size is 16 or below, only lower tests maintain the size. And when the sample size is 24, so all the 6 version of the empirical likelihood ratio tests start to maintain the size. We can see the same in the equal sample size also. Then when come to the power, so this is the power under gamma distribution. We can say that when the sample size is 24 and more, the power of the proposed empirical 6 version of the empirical likelihood ratio test is much higher compared to the remaining test. Even though here Bartlett test is having the highest power, it does not maintain the size. This is the same scenario size under T distribution with 15 degrees of freedom. This is the size computation. This is the power computation under T distribution. Then we also computed size under chi-square distribution with 4 degrees of freedom. Power with the chi-square with 4 degrees of freedom. Then finally, we summarize that in order to maintain the nominal level for empirical likelihood version and Jacquemin's empirical likelihood version, we required a sample size of minimum of 24 when the normality assumption is satisfied. For non-normal distribution, we require 28. Whereas in case of...
You have
Yes,
2
sir.
minutes.
Yes, sir, I will
2
conclude.
minutes.
Okay, sir, I will conclude. So whereas for the adjusted empirical likelihood, we require 20 for the normal and 24 for the non-normal distribution. So as a real life example, we have considered the same example used in the Ching et al. So originally it was taken from the study of FOA in 1991, which comprises of 4 groups, that is SIT, PE, SC and control group. Initially, we have validated whether the normality assumption is satisfied or not with the help of Shapiro-Wilk test. All the group shows the normality. Then we apply all the proposed test along with the existing test to check whether the equality of variance is there or not. All the tests have suggested the rejecting the null hypothesis of variance are equal, so that we conclude that variance are not equal across the group. So as a conclusion, we have proposed a 3 variety of empirical likelihood version for Leibniz test as well as the modified Leibniz test, a distribution-free approach which is with the better power. If the normality assumption is satisfied, we suggest Bartlett test and the Leibniz test for small sample. When the sample size is equal to 20 or more, we will recommend it to use the empirical likelihood version of either Leibniz test or the modified Leibniz test, especially adjusted empirical version of Leibniz as well as the modified Leibniz. It's almost similar. With adjusted empirical likelihood version of the Leibniz test perform much better. That when you come to the non-normal data, we recommended lowest test for the small sample because of its robustness. When the sample size is n greater than or equal to 24, we suggest to use the adjusted empirical likelihood version or the Jacquemin's empirical likelihood version for the equality of variances. So the final conclusion is that even though our proposed test for the small sample shows the liberal size, that means more than the nominal level, Lehman and Emerson has suggested to use the test which is liberal but with the greater power compared to the test which maintain the smaller type 1 error rate but have the less power. Therefore, he recommended to use the empirical likelihood version of the Leibniz and the modified Leibniz test, especially adjusted empirical likelihood version of the Leibniz test. These are the paper we refer for our study. So here 17 and 18 are the papers we have already published. Thank you, sir. Thank you for the opportunity.
All right. Sir, Professor Ghosh. Please unmute your mic, sir. Unmute your mic.
Yes, Satyanarayana, it's a nice talk. I appreciate. I had one question.
Thanks. Yes, sir.
You have taken adjusted empirical likelihood to test, and there you have taken one more observation. Is it like that?
Yes, sir. Yes,
now,
sir.
if you take one observation, suppose I am taking very small observation or very large observation, then it will affect the mean and variance and finally the R square. So, is there any criteria for that?
Yes, sir. Yes, sir. We need to consider a observation of the smaller order, and yes, Chen et al. Has suggested to consider a observation which will satisfy that an 1/2 log n, sir.
Then it will also very small. You are taking the log; it will be very small.
Yes, sir. So yes. Yes, sir.
High. You're taking log. It should be log 100. It is too big only. It will be very small. And it will affect the mean and variance.
Yes, sir.
And second question was this, that
yes,
you have taken for samples, one sample was the last sample was 50. Now, if you take this data, do you think that the heterogeneity will occur more? It will be heterogeneous data.
Yes, sir. So we for example, we'll have under each sample size combination, we'll generate from the variance from smaller to larger also, sir. So we are having the term while generating observation with the different variance, we are having the term epsilon. For the epsilon, we have taken the values from 0.1 to 2, which will verify that even the small sample size under small error variance, larger variance, moderate and larger variance, sir.
So you have used several likelihood ratio tests, do you heard about hierarchical likelihood ratio test? It is called H likelihood ratio
No, sir. As of now, I have not.
Well,
test, introduced by
sir.
Lee and No.
Oh, okay, sir. I will go through it. Surely, I'll go through it.
Okay, okay, okay,
I'll go
okay.
through
Thank
it.
you.
Thank you, sir.
Professor
Thank you.
Banu, Madam Banu, Madam Banu.
Yeah.
Please.
Satyanarayana, your presentation was good. You were clear in what you wanted to say. Congratulations.
Thank you, ma'am. Thank you so much.
You talked of only one application. Are there many
Yes,
more
sir.
applications?
Yes, ma'am. I have also verified with two more example given in the Ching et al. Paper where they are compared across the two group, ma'am. For example, it's the water concentration across the two types of rock also they are compared. Where also I got the similar kind of result, ma'am. I tried with two group also.
You have applicability of your work.
Yes, sir. Yes, ma'am. Yes, ma'am.
Okay.
Well, Dr. Satyanarayana, what is your contribution in this paper?
The propose of this 6 versions, sir. 3 version of Leibniz test, 3 version of modified Leibniz test, sir.
Yes, sir. The methods were proposed. The methods are available in the literature, and you have made an empirical study, isn't it?
No, sir. No, sir. We propose this for empirical Leibniz test, sir. Leibniz version and the modified Leibniz test of this kind is not available, sir.
Leibniz test was proposed by you?
Yes. No, sir. Leibniz test is there. Empirical is separate, sir. Leibniz empirical version of the Leibniz test we propose, sir.
Empirical version of Leibniz test.
Yes, sir. Empirical likelihood ratio version of Leibniz and modified Leibniz we propose, sir.
Okay, right. In what way you find it is better than the existing procedures? That you said,
Yes,
you
sir.
mentioned that the Bartlett's test is applicable for small samples.
Yes, sir.
I wonder.
Under normality assumption only, sir. When the normality assumption is not satisfied, it is very sensitive to normality assumption, sir. It won't maintain the size. Size will be kind of 0.2, 0.3 and all, sir.
That is true, because there we need the assumption of normality, definitely.
Sir. That's why.
Certainly.
Yes, sir.
But
So,
under that case, under
Yes,
the normality assumption,
yes, sir.
you mentioned that it is suitable for small samples. That's why I asked you this one.
So under normality assumption only, and it will maintain, sir. It will maintain the size as well as the power of. Because the level is
Very
more.
good.
Thank you so much.
Priya?
Thank you, sir. Thank you for the opportunity. Yes, sir. Yes.
Dr. Haripriya. Dr.
Sir, am I
Haripriya,
audible?
available? Yes, you are audible. Please share your screen.
Yeah, yes, sir.
Yes, your screen is visible.
Okay. Sir, is that visible clearly?
Yeah.
Screen is visible.
Yeah,
Please
it
start
is.
presentation.
Sir, 1 second.
It is clearly visible.
Haripriya,
Sir.
please start presentation. Your
Okay,
time is
sir.
going.
A very good evening to one and all present here. Myself, Haripriya, PhD Research Scholar, Department of Statistics, Bardiyar University, Coimbatore, under the guidance of Dr. I. Jaishankar, Professor and Head, Department of Statistics, Bardiyar University. I'm going to do my presentation on a fuzzy approach to Calfish Prentice estimator. This is the outline. 1 second, sir. I think. 1 second, sir, please.
Yes, Haripriya.
Sir, actually some issue I can't able to move my slide. 1 second, sir, please. Sir, is it visible now clearly?
Is it visible, madam? Please proceed.
Okay. This is the outline of my presentation. It includes the introduction, methodology part, following by the numerical illustration, results and discussion, conclusion, and the reference. Introduction. Survival analysis encompasses a wide range of techniques that analyze the time taken for a specified event to occur in living beings or working objects from a fixed approach. Hence, the survival analysis is also called time to event data analysis. In a survival analysis, the variable is usually referred as survival time because it gives the time that an individual has survived over some follow-up period. Most of the survival analysis must consider a key analytical problem called censoring. Censoring occurs when only some information about the individual survival time is available, but the exact survival time is not known. More about the preciseness and impreciseness, it is quite natural that sample observation are collected for statistical analysis of any nature. Whether to estimate parameters or to test the hypothesis are often taken as precise numbers. However, it is unreasonable to describe genuine continuous variables as precise integers and vectors since accurate measurements are not possible in many practical situations. In survival analysis, lifespans are continuous and may not be accurate, and they are more or less ambiguous. A potential arena for dealing with such inequalities, which may be prevailing in data, which is fuzzy theory. Hence, involving fuzzy approaches to traditional statistical procedures may be more relevant and realistic, in particular for analyzing survival durations. What is a fuzzy number? We can call it as a mathematical term that is used to express quantities that are somewhat ambiguous or hazy rather than exact. A fuzzy number is defined by a range of probable values and a membership function that shows the likelihood that each value in the range belongs to the fuzzy number, in contrast to a classical number, which has a single discrete value. A set of values of some characteristic x arranged together with their corresponding membership functions constitute a fuzzy set for a particular criteria. Every conceivable value of x is mapped to a degree of membership in the interval 0, 1 by the membership function nu of x. If it is 0, then it indicates that x does not belong to the fuzzy set. If it is 1, it indicates it is a complete member of the fuzzy set. And if it lies between 0 to 1, then it is a partial member of the fuzzy set. Various types of fuzzy numbers exist according to the need to represent different forms of uncertainty, vagueness, and imprecision that occur in many real-life situations. Naming a few, there are triangular fuzzy numbers, trapezoidal fuzzy numbers, Gaussian fuzzy numbers, piecewise or custom-wise fuzzy numbers, etc. In which here we concentrate on the triangular fuzzy number, which is more versatile and computationally efficient for representing many phenomena. The basic format for the triangular fuzzy number is of the form ABC, where A is the lower bound of the fuzzy number and B is the peak or most likely value and C is the upper bound. This is the membership function we can define for the triangular fuzzy number, in which if the membership 0, then it indicates x lies outside the range of the fuzzy number, and if the membership lies between 0 to 1, it lies between A to B, it increases, and if it lies between B to C, then it decreases. The alpha cut is a crisp value that is created by taking all of the elements whose membership degree is greater than or equal to a given threshold alpha, where alpha is between 0 and 1. The mathematical definition for alpha cut is given as follows, where alpha equal to 0, the alpha cut encompasses all elements possessing any non-zero membership, thereby representing the support of the fuzzy set. For alpha equal to 1, the alpha cut represents the core of the fuzzy set, wherein the membership degree is precisely 1. The alpha cut of a triangular fuzzy number is given as follows, where AL alpha is the left endpoint and AU alpha is the right endpoint. Literature review. The importance of the subject of survival analysis hails from the fact that it analyzes the data concerned with the lifetime of living beings. Though lifetimes are random variables that can be characterized by some probability distributions, a major hurdle for analyzing the survival data is the problem of censoring, because of which scientists prefer non-parametric methods. One among such methods is due to Kaplan-Meier in 1958 is the most familiar and could be used in case of heavily censored data and estimate the survival function by means of the conditional probabilities, which are obtained based on censored and observed events with the assumption of independence of censored and survival times, non-informative censoring, and homogeneity of risk. Nelson Allen in 1972 proposed another non-parametric estimator that estimates the cumulative hazard function. The main drawback of these estimators is that they could not incorporate the covariates. Cox in 72 suggested a procedure for estimating the hazard function based on the proportional hazard assumption and linear relationships with the covariates. Breslau in 72 suggested a formula which could be used as a baseline hazard function in the Cox regression model. Breslau model works well for the large data set with few ties and even times are approximately continuous. However, it is not suitable when the ties are more frequent and the even times are truly discrete, may introduce bias in such situations. To overcome these limitations, Kalplish-Prentice 1973 proposed an alternative for estimating the baseline hazard function which works well even with a small data and frequent ties. In survival data, the survival times are mostly continuous in many cases. However, they are recorded discrete more often. It is evident that the continuous observations are more or less fuzzy, and the same is also applicable to survival times, Whittle in 1995. When the survival times are influenced by certain covariates of continuous nature, they may also be considered as fuzzy. Hence, apart from randomness, the fuzziness present in the data should also be accounted and addressed in order to get more reliable survival or hazard estimates. In this work, an approach is suggested to incorporate fuzziness in Kalplish-Prentice estimator. The KP estimator is a novel estimator which estimates the survival function using discrete failure times to approach continuous function developed to address the lacuna of Kaplan-Meier on its inability to adjust for covariates. Hence, it may be considered as a counterpart for the Kaplan-Meier estimator. Kaplan-Meier has a wide application in survival analysis and computing this model for estimating the cumulative incidence function for measuring the probability of specific event type. The equation for the KP estimator survival function is given as follows. The methodology here adopted is, let me consider the time points as T1, T2, etc. Tm represents the survival times for M subjects. As stated earlier, the survival times are continuous in nature but recorded as discrete quantities, hence they are more or less fuzzy. This kind of fuzziness is to be addressed together with the inherent randomness present in the data for any type of analysis. In this paper, a methodology has been proposed to fulfill this objective of Kalplish-Prentice non-parametric survival estimator. This procedure for the same has been given below. In the first step, we converted the survival times into triangular fuzzy numbers. As mentioned earlier, a triangular fuzzy number consists of mainly 3 points, one minimum possible value, most likely value, and the maximum possible value. A similar procedure of classification number is to be adopted for the covariates which continues in nature by converting them also into the triangular fuzzy number. Methodology, let nu delta I be the membership function of the falsified survival time that assigns a degree of membership to each of the time point which ranges from 0 to 1, where 0 indicates no membership and 1 indicates full membership. The falsified survival time can be represented as follows. After converting the survival times as well as the continuous covariates as fuzzy numbers, alpha cuts of each of them for a specified level of alpha were found. A crisp interval, this is called the alpha cut for the given triangular fuzzy number. The alpha cut for survival can be represented as follows. After these alpha cut values are defalsified using centroid method. The equation for calculating the centroid method is given. So also to the case of falsified covariates of the model was done using the defalsified values. The Kalplish-Prentice estimator was calculated with the help of Python software, and the results obtained may be combined with the classical Kalplish-Prentice estimator. Numerical illustration. A data set was taken from the textbook, actually, from Biostatistics, a foundation for analysis in health sciences by Chad L. Cross. The data represents a self-reported time in weeks of the occurrence of relapse or the time at which the patient was lost to follow-up. Patient status is mentioned as 0 for censored and 1 for relapse. The drug of choice is denoted as 1 for opiate. It is a painless drug, and 2 for painkiller drug, and 2 for the other drugs. The patient's age was also taken as an additional covariate. The methodology proposed for fuzzy KP estimator is adopted for the above data. Here we consider the alpha cut value as 0.2. So, the curves of both the survival and hazard functions for the classical KP estimator as well as the falsified KP estimator are illustrated below for the comparison. Figure 1 is the comparison for the classical and falsified survival curves along with the median survival representation for the median survival times, and figure 2 is the comparison for classical and falsified hazard curves. it can be observed that from figure 1 and 2, there is a subtle difference that
And
exists
meeting
both the survival and hazard curves before and after falsification. The median survival time observed using classical KP estimator was found to be 19, which is greater than that of one observed through falsified KP estimator, which is 16.29. To test whether is there any significant difference exists between the survival curves obtained from the classical KP estimator and its falsified version, the Lagrange test procedure was adopted with the null hypothesis that the curves are similar.
Dr.
The
Haripriya,
Lagrange test-
you have two minutes.
Okay,
2
sir,
minutes.
okay, sir. Yes, sir. The p-value is 0.141, which show there is no much significant difference. But however, it depends on the selection of falsification factor applied for falsification. The full impact of the KP estimator can be explicitly revealed when we apply that to the Cox model. Results and discussion. When a statistical analysis is conducted using the data observed from a random sample, it is crucial to take into account both the randomness and the fuzziness of the data, especially when the data are continuous. This is even truer in the case of the survival time. Based on this truth, a falsified version of KP estimator was found and the corresponding values of the survival or hazard function are estimated. The assimilation of the fuzziness may take the model more realistic and hence produce accurate results, since any observation of continuous nature tends to exhibit ambiguity. Ignoring this would lack to reliability of the results obtained from any type of analysis. Conclusion. This study introduced falsification methodology and examines its implications concerning the KP estimator. It is observed that estimates of survival probabilities and the survival curves exhibit differences when falsification is concerned. Median survival time for the KP, classical KP and the falsified KP shows much difference. Hence, the result obtained can be regarded as more reliable since it considers both fuzziness and the randomness. It is also noted that the nature of the survival data, the event, and the researcher's viewpoint should also be taken into consideration when choosing the falsification factor in this case. These are my references. Thank you.
Very good, Haripriya, for keeping in time. The question is, what is the need for falsification when it is not required? When the data is very clear, what is the need for falsifying it?
Actually, falsification, we implement it on if we are not certain or we are having that imprecise
Yes, only when we are not certain, you can apply that. But
Yes,
what is
sir.
the need for very clear data, regular data for falsifying it?
For example, if you are in case of a survival data, sir, if a patient is died on particular time, we can't able to exactly mention that it's on. For example, for 10 o'clock, we can surely say we can't able to say surely that it is up to 10 o'clock or like
Madam,
maybe
the data is very
9:50.
clear. The data is very clear, and there is when there is the measurements are made appropriately. Of course, all the measures are subject to error. That is known.
Yes, sir. Yes, sir. Yes, sir.
That is not the way to claim that falsification is required.
Yes, sir. Yes, sir.
Right. And the other one, how do you claim that your estimator performed better?
Actually, I have done the comparison with the other estimators in Cox model like Breslow and Fleming-Harrington estimators.
What
In the-
what measurements you have taken? What measures you
sir?
consider for comparison?
In this particular paper, we just deal with the two same data set using classical and the falsified approach using that median survival time. That is the quantity we have taken
you
to
did
compare.
not. Well, you did not take up the question. Well, Professor Ghosh.
Yeah. I was surprised with your presentation. Once you are talking about Kaplan-Meier method, then you are talking Cox proportional hazard regression model. After that, you are talking fuzzy method. Then you are talking KP methods. What you want to say, it is not clear for me. Now, my question is yes, because there we need loss of person, death of person, and available person for the next year. But your case in the fuzzy method, which you discuss, or the KP method, it is just for the same years, and survival we required for the at least 4 or 5 years back. So I didn't understand why you are using the fuzzy method. And what is the advantage of KP method, the Kaplan-Meier method, or the Cox proportional hazard regression model?
Sir, Kaplan-Meier method is the basic non-parametric method we are having for dealing with. Sir, we are having for the non-parametric survival analysis. In Cox method, we generally use this Kaplan-Prentice estimator, that is the KP estimator or the Breslow estimator or the Fleming-Harrington as the baseline model only. After that, we are calculating using that Cox regression model, sir. This paper is generally, I have done the initial approach for classification of that particular non-parametric method. And it is showing that fuzzy
I don't think fuzzy method will be more applicable. Fuzzy method will be more applicable than the Kaplan.
Hello?
Mere method, or I don't think.
Sir, actually your voice is breaking, sir. I'm not clear.
Thank you. You have less time. Let us go to Dr. Bhanu.
Well, Dr. Bhanu? Professor Bhanu?
Yeah. Yes, sir. You
Yeah.
mentioned, Haripriya, that survival times are influenced by certain covariates of continuous nature. Does
Yes,
that happen in this case, in your case also?
Yes, ma'am. Actually, we consider age as another covariate here.
Huh?
We also calculated, we also converted that covariate into fuzzy. Then we had done this study, ma'am.
So they,
Both the
you-
time and the covariate has been specified, ma'am, actually.
Okay.
Well, thank you, Dr. Haripriya.
Thank you, sir. Thank you.
Dr. Ramyanath? Dr.
Yes, sir.
Ramyanath,
Yes, sir.
please share your screen and start presentation.
Okay, sir. Am I audible, sir?
Yes, you are audible.
Good evening, one and all. I'm Remya Nathpi. I'm going to present on Bayesian spatiotemporal modeling of breast cancer incidence risk and its association with air pollution. These are the overview of my work. Introduction. Breast cancer is the most commonly diagnosed cancer and leading cause of cancer death among women globally. In 2022, an estimated 2.3 million new BC cases were reported worldwide, accounting for 11.6% of all cancer cases and 6.9% of cancer death. In India, BC incidence shown a significant upward trend with a 39.1% increase in age standardized incidence rate from 1990 to 2016. Thiruvananthapuram, one of the major cities in India, has a very high BC incidence rate, showed a significant increase by 5.1% annually. BC accounts for 31% of all cancers among females in Thiruvananthapuram and 35% of patients are under 50 years. BC risk is influenced by several well-established individual-level risk factors such as early age at menarche, late age at menopause, late age at first childbirth, decreased duration of breastfeeding, and lifestyle transition like physical inactivity, obesity, etc. Aggregator-level factors like environmental exposures have also been found to affect BC risk. Some studies have reported an association between BC risk and outdoor air pollutants such as NO2, PM2.5, and PM10. To assess these aggregator level factors, spatial analysis is crucial as environmental pollutants vary by locations and accumulate increasing disease risk with prolonged exposure. Spatiotemporal models help to identify geographic patterns of these disease risks, understand how risks evolve over time, pinpoint higher risk areas based on local factors. Bayesian spatiotemporal models with conditional autoregressive priors are effective in capturing these complex patterns. Present analysis focus on three Bayesian spatiotemporal models such as BST-curve first-order autoregressive, second-order autoregressive, and separated spatial model to investigate the association between air pollutants and BC incidence. These are the materials that I have used here. The study area is the Thiruvananthapuram Taluk, consisting of 29 administrative units. The study period is 2005 to 2019. Due to small number of cancer cases reported annually, we have taken temporal aggregation of 3 years from 2005 to 2019. That is, our study period is divided into 5, such as 2005 to 2007, 2008 to 2010, etc. 4370 BC cases were collected from population-based cancer registry Thiruvananthapuram and air pollution data from Kerala Pollution Control Board. Pollutant concentration at unmonitored locations estimated using inverse distance weighting spatial interpolation techniques. Then we have used Google Earth software for geocoding the addresses of BC cases that we have already collected. Then study area boundaries of Thiruvananthapuram Taluk were sourced from Divaj's database. Then ArcGIS and SATScan used for space-time analysis, and software R was used for spatio-temporal modeling. First, we have checked whether there exists any kind of spatial autocorrelation in the study area. For that, we have used global and local spatial autocorrelation techniques. First, we have used Moran's eye to test whether there exists any kind of clustering in the study area globally. If any kind of clusters was observed, then we go for Gettys or General G to identify whether the obtained clusters are of high values or low values. Then we go for a local spatial autocorrelation technique. That is because even if there does not exist any kind of clusters globally, there still exist clusters locally. So for that, we have used local Moran's eye statistic. Local Moran's eye statistic identify not only the local clusters but also the outliers. An outlier means a high value region is surrounded by low value regions. Then we done an hotspot analysis using Gettys or General GI statistic to identify the exact locations of the clusters obtained. A hotspot is defined as a region with a high value surrounded by high values, and a cold spot is defined as a region with low value surrounded by low value regions. Then Kullrow space-time scan statistic based on a discrete Poisson probability model was used to detect temporal and space-time clusters. The window with maximal likelihood is defined as the most likely cluster area, and other statistically significant clusters were identified as secondary potential clusters. The test statistic is given by this, and then for obtained each cluster, we have calculated the relative risk as follows. An initial Poisson generalized linear model was performed to study the effect of available covariates in assessing spatio-temporal autocorrelation. First, the study region is partitioned into 29 non-overlapping areal units, and data are observed for each unit for 5 consecutive time periods. The response data are denoted by Y, which follows Poisson distribution with EKT, theta KT, where theta KT is the risk as modeled as XKT transpose beta, where theta KT is the risk, EKT is the expected count, and XKT denotes the covariates, and beta is the coefficient vector. After fitting Poisson generalized linear model, if still persists spatial autocorrelation in the residuals, we go for Bayesian spatio-temporal models. As our disease outcome variable is count, the general form of Bayesian spatio-temporal models is given as YKT follows Poisson theta KT, where the log theta KT is expressed as XKT transpose beta plus psi KT. Here psi KT denotes the random effect which combines components that capture spatial, temporal, and space-time interaction. Different structures for psi KT have driven the creation of diverse spatio-temporal models. Since the goal of this study is to estimate the extent to which the spatial variation in the response has changed over time, we have applied 3 Bayesian spatio-temporal models here. Here, Carr-Pryor is incorporated for spatio-temporal random effect, where the temporal correlation is modeled through an autoregressive mean decomposition and spatial correlation by precision metrics inheriting neighborhood structures. This is an overview of the AR1 model. Here, we estimate the evolution of spatial random effect surface over time. Here, the spatial random effect, the random effect psi KT is denoted as spatial random effect phi KT, where phi KT is modeled as normal Carr-Pryor with a mean rho t phi t minus 1 with variance tau square QW rho s inverse, where QW rho s is the precision matrix as defined below. Here, the first spatial surface is modeled as normal Carr with a mean 0 and variance tau square QW rho s inverse. Here, the variance parameter tau square follows inverse gamma AB, and the spatial correlation parameters, spatial and temporal correlation parameters rho s and rho t follows uniform 0, 1. This is similar to AR2 model. In addition, an extra parameter for AR2 model, that is rho T1 and rho T2. This is a separated spatial model. This is used to estimate a common overall temporal trend and evolution of spatial random effect surface over time. Here, psi KT is denoted as phi KT plus delta T, where delta T is a temporal effect common for all areas. Here, the spatial effect for each time period is modeled as normal Carr-Pryor, and temporal effect is also modeled as normal Carr-Pryor. Here, the variance parameters were all follows inverse gamma distribution, and spatial correlation parameters follows uniform 0, 1. Then results. A total of 4,370 BC cases were recorded from 2005 to 2019 with the crude rates as 36.8 to 43, etc., up to 60.78 for the time period 2005-7, 8-10, etc., up to 17-19 respectively. An average of 52% of administrative units had rates exceeded 50 in each 3-year period. However, the distribution of BC varied greatly between administrative units ranging from 0 to as high as greater than 90 each year. The urban areas with high incidence rate showed a significant trend increase from 41.76 in 2005-7 to 72.31 in 17-19. This is a spatial distribution map of the crude rates. The darkened region shows with high crude rates. As we can see, as times goes on, the regions with high crude rate is increasing. This is a symptom of existence of a cluster in this area. So that we go for spatial autocorrelation techniques. For that, first we already said we have used global Morenci. The results of global Morenci says that there exists a cluster. So we go for a general JETIS or general G-score, which shows these clusters are of high clusters. Then we go for a hotspot analysis to locate where these clusters were obtained. In the figure from A to E shows the hotspot analysis of the respective years. The shaded region, the darker region shows the hotspots that these hotspots were obtained in the urban areas respectively. Then we have conducted a local Morenci test, which is given in the figures from F to J for each respective years. The local Morenci result were in correlation with the hotspot analysis, indicating the presence of hotspots in the urban areas. Then, the most likely spatiotemporal cluster using Kulros SAT-scan was located at the urban area itself, and high risk period was from 2014-16 to 17-19. 1,432 BC cases were reported in this area during this period with a relative risk of 2.10. The point estimate and p-values of all covariates initially exhibit significant effect on incidence, and air pollutants such as PM2.5 NO2 being associated with an increased risk. To quantify the presence of spatial autocorrelation in the residuals, we computed Morenci statistic of residuals for each year. The test shows strong residual spatial autocorrelation with the Morenci value 0.12, etc., 0.21, 271, and a p-value of less than 0.05. Then we go for Bayesian spatio-temporal car models. Here, all the three models were run in R programming using car-based ST package using MCMC with 220,000 iterations. Convergence of Markov chains were ensured using trace plot, comparing result from multiple chains and potential scale reduction factor. I have given a sample of the trace plot that I have obtained. The models were then compared in terms of lowest values of deviance information criterion and Watanabe-Akaike information criterion. These are the results of the models that I have obtained. Here, the BST car AR1 model had substantially better model fit as demonstrated by the smallest DIC and WIC followed by AR2 and separated spatial model. The separated spatial model had the largest DIC and WIC. Then, based on the obtained model, the relative risk were estimated. This figure shows the relative risk estimate from the year 2005-7 to 2017-19. From the figure itself, it is clear that the relative risk was increasing over the years, especially in the urban areas. The spatial parameter obtained is 0.50 and temporal parameters, value of temporal parameter is 0.91, which show relatively high values indicating the presence of both spatial and temporal autocorrelation in the data even after adjusting for the covariates effect. Under this model, the average yearly concentration of PM2.5 and NO2 had a significantly positive correlation with BC incidence during the study period. Here, the estimated relative risk and 95% credible interval associated with a unit increase of each pollutants were provided in the following table. From the table, it is clear that the variables NO2 and PM2.5 had significant effect on cancer incidence, and other variables does not find that much significant. Then we go for a sensitive analysis to examine the robustness of the results. Three distinct priors for the variance terms, namely inverse gamma 1, 0.01, 0.5, 0.005, 0.001, 0.001 were used. The observed variations were minimal, indicating the findings were not significantly influenced by the choice of hyper priors. Hence, we selected inverse gamma 1, 0.01 prior owing to lower model fitting DIC and WIC values. Then discussion. Assessing spatial exposure to environmental factors is essential for understanding patterns in disease incidence. Patient spatiotemporal models incorporating conditional autoregressive priors are widely used to analyze these spatiotemporal patterns and identify high-risk areas influenced by local risk factors of cancer. BST models in cancer studies are proved to be beneficial and provide more convincing evidence of true variation than separate spatial or time series analysis. Based on spatial autocorrelation technique, we observed significant global spatial autocorrelation indicated clustered patterns of BC incidence, with hotspot analysis identifying high-risk clusters predominantly in urban regions. The Kulrov retrospective scan statistic detected significant spatiotemporal clusters of higher BC incidence, often coinciding with areas of high population density and elevated air pollution. Among different
Ramyanath, you have 2 minutes.
Okay, sir. Among different BST car models tested, the AR1 model emerged as the best fit, effectively capturing the spatiotemporal variation in BC incidence and identify high-risk areas. By analyzing disease patterns over time, we observed an upward trend in the risk of BC incidence with a significant association with air pollutants such as PM2.5 and NO2. Spatial analysis identified clusters of high BC incidence in areas with elevated levels of these pollutants. Several studies suggested this kind of association between outdoor air pollutants and BC risk. Although the precise biological mechanism linking air pollution to BC remains unclear, the possible association may be attributed to the processes such as oxidative stress, DNA damage, and inflammations caused by the air pollutants such as PM2.5 and NO2. In conclusion, this study demonstrates the effectiveness of BST modeling techniques for risk estimation in addressing both spatial and temporal effects in BC incidence. Further studies are needed to validate these findings across diverse populations, explore causal mechanisms, and assess the impact of other risk factors on BC risk. These are the references I have used. Thank you.
Thank you. Thank you for presenting on time. Professor Banu?
Yeah,
Professor
good
Banu?
presentation, Ramya.
Thank you.
The only thing is that my observation or whatever we have learned so far, that breast cancer is usually genetic in nature. If a mother has got breast cancer, the daughter is usually at a higher risk.
Yes, madam.
Yes. Madam, pose your question.
Is it? Hello? Ramya?
Madam, yes, madam. Yes, madam, you are audible.
Study is restricted only to Trivandrum.
Yes, madam.
Yeah, so maybe some more studies are required to make it global,
Yes, madam.
or maybe to cover the entire India.
This is because, madam, availability of data is a problem, madam. We have a well-established cancer registry so that we get these kind of cancer information.
And you have said that there is a possible association, there could be a possible association between these two factors, PM 2.5 and NO2. Maybe other factors may also be playing a role in that.
Yes, madam, of course.
Yeah, okay.
Professor Ghosh?
Mr. Ramya, see,
Yes, sir.
I have not agree with you that breast cancer is affected by environment. I have taken a data of 15 years of Saurashtra region of Gujarat state by taking a project from DST of 30 lakhs and produced 2-3 PhDs on this, and I never found that the environment is affecting the breast cancer. What effect? Effect is the stage. If the patient goes to stage 3 and 3B, somehow doctor, by giving radiotherapy, hormone therapy, and surgery, they survive for 5 to 10 years. If they go for the 4A and 4B, they will never survive after 2 years. But they go stage 1, then by treating all these therapies, they survive and still they are surviving. So I am not agree. First question. Second question, you are using autoregressive. Just for sake of some work, you are using autoregressive. Autoregressive never used for the breast cancer. Only the logistic regression, that is the multinomial logistic regression, I advise you to use it. And from there only we can, and you are using autoregressive just for sake of something we have to do, you are doing it. This is wastage of time, yours and also others also.
Dr. Ramyanath? Ramyanath?
Yes,
Please
yes,
answer
sir.
me.
Yes, sir. Sir, here we are actually doing spatial analysis so that we have used these kind of models. In spatial analysis, we didn't use this kind of logistic regression. That is why.
See, in breast cancer,
No,
there is
Dr.
no need of
Ramyanath, you
stress-
please
stress
understand what
analysis.
Professor asked the question. you understand the rationale behind the question. Sir raised the question, very serious one, that application of autoregressive model for breast cancer. That is an important one. And Sir has also expressed his experience regarding the impact of
environmental effect.
socio-temporal. So you please, it is a very serious comment. You please address this.
Okay, sir.
Only the stage effect is there.
Okay.
Yes.
Do you have any answer for this?
And some diets.
No. Okay. Right. Sir, she doesn't have an answer for this.
Okay, thank you, sir.
Now, the Ramyanath,
Yes, sir.
I have a few things to ask. That you have used 1 minute. You have used the Bayesian procedures. You have used the Bayesian procedure, right? And
Yes,
you have
sir.
used some priors. How did you evolve the priors?
Sir, this is an application of
Application
normal.
point of view, you please take care of. I also have the same doubts regarding that application of autoregressive model of breast cancer time series data, right? That you do not have answer. But my question is related to the applications of statistical procedures. You applied the Bayesian procedure and you have made an assumption about the prior, and the prior has certain parameters. They are called hyperparameters. How did you
Yes, sir.
evolve the hyperparameters? What procedure you followed it?
Okay, sir. First of all, I have used normal Karpov spatial effect, spatial surface effect. Since tau square, I have used inverse gamma for the variance parameter tau square. Since tau square is a variance parameter, variance of normal Karp prior, gamma, inverse gamma is a conjugate prior of normal distribution, and it can
No, not necessarily. Did your data suggested you to choose inverse gamma? Did you
No,
have
sir.
any information regarding application of inverse gamma for your situation?
No,
Or
sir.
you have chosen as for the flexibility of mathematics?
Flexibility of mathematics is one of the reasons, sir. Since it is a
Okay.
conjugate prior that we are usually used, that's why I have chosen
I
it.
understand. That is the reason why I asked, because inverse gamma prior is a natural conjugate prior for sampling from the normal population. True, right? But what your data suggested, that accordingly you could have made an assumption about the prior. And the second one, when you make an assumption about inverse gamma prior, how did you evolve the hyperparameters? The parameters in the inverse gamma distribution.
Yes, inverse gamma distribution, I have used parameters values as 1 and 0.01.
No. You have taken hypothetically. Good. You have taken hypothetically.
Dr. Loganathan, I have one more question to her. I had one more question to her.
Oh, please,
Yes.
please.
And Dr. Remya,
Yes, sir.
did you find what are the cause of breast cancer?
Yes, sir. You mean environmental cause or?
No, environmental I am not agree. Anything
sir.
else? Anything else?
Yes, sir. Reproductive changes in the reproductive patterns, that is a late age of early age of menarche, late age of menopause, decreased duration of child breastfeeding, then obesity, physical inactivity. These will all.
Did you study about the number of children affecting the breast cancer?
Yes, sir. It's also a genetic.
This is the main this is question.
Yes, sir. I didn't get you.
Did the number of children affecting the breast cancer?
I didn't consider, sir.
You didn't consider. Okay, then okay.
Okay.
Thank you.
Right. Thank you, Dr. Ramyanath. Let us call the next competitor, Dr. Sarath Sindhu Mukhopadhyay.
Yeah. Good evening, sir.
Share your screen.
Yeah. Is it visible?
Visible.
Hello.
Visible. Proceed.
Okay.
Yes.
Okay. Good evening, everyone. I am Mr. Sarath Sindhu Mukhopadhyay. I am a senior research fellow in SQC and Word Unit, Indian Statistical Institute, Bangalore. And thank you for giving me the opportunity for presenting my paper in the second round of the best paper competition. The work I am presenting is inference based on a novel failure rate based multiple step stress dependent competing risk model and co-authored with Dr. Owen Pal from University of Bardwan and Dr. Jijo Ivi from University of Institute, Bangalore. So these are the basic outline of my work. And so basically, the lifetime of products has been prolonged due to the advancement of science and technology, especially for the electrical and electronic units. And so traditional life testing does not work in that case because products does not fail easily. That's where accelerated life testing has come into the picture. So stress accelerated life testing is a special kind of ALT experiment where test units are initially exposed to low stress level and gradually they are exposed to higher stress level and failures happen. And it is stopped after a certain time or certain number of failures. So to connect the CDFs of defined stress levels, generally there are very many popular models like cumulative exposure model, failure rate-based model, tempered random variable model, tempered failure rate model, cumulative Briggs models, etc. So also in real world scenario, whenever a failure happens, failure of a product happens, the failure happens due to the multiple causes. So in that kind of situation, a separate analysis for defined causes are also necessary. So this kind of problem is called competing risk problem. And in competing risk problem, it is a usual assumption in literature that the risks are independent, but this is unrealistic in practical because if we consider a airplane with two engines, so suppose one engine breaks down, then automatically the pressure on the remaining engine increases, so that engine also fails sooner, and that's why interdependence automatically come. So in our work, we have used a distribution is proportional hazard class of distribution. So it's a generalized distribution. CDF is given by this, where F0 is a baseline CDF of any distribution with one parameter alpha. And so from there we can find the PDF also, just differentiating the CDF. And so there are many studies on the independent competing risk setup, but there are very limited number of studies that works on dependent competing risk setup and under multiple steps accelerated life testing. So generally for interdependence, bivariate and multivariate distributions are used and they're popular. And recently one work has done by Bai et al. That they have worked on multiple SSLT for type 1 censoring scenario for Marshall-Alkin bivariate exponential distribution. And they have considered a cumulative exposure model to connect the CDF of defined stress levels. So we have taken the setup as multiple SSLT, dependent competing risk data, and under we have taken the censoring scheme as progressive type 1 censoring, and we have used a Marshall-Alkin bivariate proportional hazard class of distribution, which is more flexible because it can take care of increasing, decreasing, upside down, or bathtub, upside down bathtub, or bathtub curve of hazard rates. So the genesis of the bivariate class of distribution is like that. Suppose we have three independent distribution, U0, U1, and U2, and all are proportional hazard class of distribution with parameters alpha, lambda naught, lambda 1, lambda 2. And if we take T1 and T2 as minimum of U0 and U1 and T2 as minimum of U0 and U2, the joint distribution of T1 and T2 will be called Marshall-Alkin bivariate proportional hazard class of distribution. So it was first introduced by Marshall-Alkin, and then it has been widespreadly applicable in competing risk theory and reliability studies. So if you change the baseline as a survival of exponential or standard exponential, you will get Marshall-Alkin bivariate exponential. Similarly, you can get Marshall-Alkin bivariate variable for e to the minus t to the alpha for 1 plus t to the alpha whole to the minus 1. We will get Marshall-Alkin bivariate bar 12, and e to the power 1 minus e to the alpha we will get Marshall-Alkin bivariate chain distribution, which are well studied in the literature. And the censoring scheme we have taken is progressive type 1 sensor. Suppose at the beginning, suppose at time tau not equals to 0, we put n items into the experiment, and after at tau 1 we get that there are n1 failures in between that, and we have the failure times, and out of n1 failures, suppose n1 failures happens due to the cause 1, n1 failure happens due to the cause 2, and n10 failure happens due to the failure of the simultaneous causes. So at tau 1 we remove R1 items and we go to the stress level 2, and there are n2 failures, and similarly we go up to m stress level, suppose. And so this problem can be studied or can be viewed as a failure of series system with dependent component where T1 and T2 are the failure times of the two components. And suppose for the particular stress level SI, suppose Ti, I1 and Ti2 are the failure times, and we have assumed that Ti1 and Ti2 follows Marshall-Alkin bivariate proportional hazard class of distribution with parameters alpha, lambda I0, lambda I1, and lambda I2. And we have taken another assumption that the power law assumption that the scale parameters of different stress levels are connected through lambda ik equals to ck into si to the power p, and lambda I, which is summation of lambda ik, is c0 plus c1 plus c2 and to si to the power. So basically we cannot observe the failure time of both the components. We can observe only the minimum time of both the components, or minimum time of both the causes. So we have defined t is minimum of t1 and t2, and we also indicate we have two indicator function, that is delta 1, delta 2. Delta 1 is 1 whenever t1 is less than t2, and delta 2 is 2 whenever delta 2 is 1 whenever t1 is greater than t2, and also when delta 1, delta 2 is 0, 0 whenever both the failure happens. This is the unique case in our work. Also is at stress level si. So basically there are two risks, so t1 and t2, and so we can see the random variable as t, which is minimum of t1, t2, and delta 1 and delta 2. And before going to the likelihood function, we'll define one theorem that if t1, t2 follows Marshall-Walker bivalent proportional hazard class, then t1, t2 both are marginally also proportional hazard class of distribution, and minimum of t1, t2, that is t, that is also proportional hazard class of distribution with this parameter. And also we can see that delta 1, delta 2 follows multinomial distribution, and the minimum failure time and delta 1, delta 2 are independent. This can be proof. I have not shown the proof here. And we have taken up to connect the stress levels of different stress levels, the CDF of different stress levels. We have taken a hazard rate based model, because which is more tractable than cumulative exposure model. So here basically hazard of any stress level is proportional to the baseline hazard. And also from this hazard rate, we can transform this into the CDF, which will be look like this. And from that, our data is t, and delta 1, delta 2 has t is the minimum of time, and there will be parameters will be alpha and all the lambdas for different stress levels. And likelihood can be constructed using multiplication of which is proportional to multiplication of likelihood at different stress level. So if we consider the power law model as all the lambdas are function of p, c0, c1, c2, the parameter space will be shrink to only 5 parameters, and from there we can find the log likelihood function, and the log likelihood function will be look like this. And if we differentiate the log likelihood function with the parameter space, we will get the score vectors. Differentiating the score vector, we will get tr equals to 0, and we can get the estimates, but because there are 5 parameters, that is also a hard problem. But if we first differentiate with respect to C0, C1, and C2, we can get some closed form, which is a function of alpha and p. We can put that in the likelihood function, and we can find the profile likelihood function, which is a function of alpha and p only. And from the profile likelihood function, we can get what is the alpha hat and p hat, and going back to the, we can put that estimate in the ck hat, and we can get the estimate of C0, C1, and C2. So similarly, we can get the approximate confidence interval for large n. So, and the distribution of estimated parameters will be given by this equation, where I theta is the Fisher information matrix, which can be obtained by the derivative of the second order partial derivative of the log likelihood, and evaluated at the estimated parameter value. And from there, we can find the confidence interval of each parameter. And if we need any more thing, like other than the parameters, like reliability at some other value or some other calculation, using delta method, we can find the estimates of those parameters also. And so we should note that it was a 3m plus 1 dimension problem, because for each stress level there were 3 lambdas, lambda naught, lambda 1, lambda 2, and so 3m and alpha is there. We have considered alpha is same throughout the experiment, which is the failure shape of the failure or failure mechanism. And if we take the power law, it will be a 5-dimensional problem. Now if we go to the profile likelihood method, we will have only, it is a 2-dimensional optimization problem. And so for validation, we have done extensive simulation studies for different distributions, like for Marshall-Walker bivariate Weibull, BART12 and chain as baseline. And we have taken 3 stress level, and S1, S2, S3 given by these values. And so there are 5 parameters, and we have considered n is 40, 60, 80, and 120. And for the removal scheme, we have taken R1, R2 as like this values, which is the removals at tau1 and tau2. And for different distributions, like for Marshall-Walker bivariate Weibull or BART12 or chain, we have taken these values to show the simulation. And based on the simulation tables, we can show that first progressive type 1 sensor data were generated, and based on 10,000 Monte Carlo simulations we have done, and MLEs and other estimates are calculated. So from that we can see that absolute estimate is the close to the true parameter value, and mean square error also decreases for as n increases. So which shows the consistency of the post estimation method. We have also find the coverage probabilities of the model parameters which are close to the nominal values, and we have shown the average length also, which also decreases as n increases. But for scheme 1, where there is no removal, for that we get the best result in terms of MSE and ALs. And a real life data which I talked about before, that the electrical connector data, which has two kind of failure, mechanical failure and contact failure, has been discussed. And these are the temperature for the 3 stress levels are there at which the experiment was done, and 45 degrees the standard working temperature, and tau 1, tau 2, tau 3 are given by these values, and n is 64, out of which 9 units are censored at the end. And first we have done the TTT plot. TTT plot is total time on test plot, is the empirical plot to show that what should be the hazard rate. We can see that from the TTT plot is the increasing hazard rate. And for the, we have fitted the distributions like MOB, MOBW, MOBCH, MOBVXI. So, and for that, as there are no alpha in MOB, we can do a plot like this, P versus log likelihood. We can see the unimodality of the, for exponential distribution. So similarly for alpha and P, like for MOBW and MOBCH and MOBVXI, so we can see the unimodality of profile likelihood for all other distributions like Weibull chain and Barth-Webb distribution. And you can see that they have unique solutions. And we have done a empirical versus theoretical fit for MOB distribution.
Sarat Sindhu Mukhopadhyay, you have 2 minutes.
Okay, sir. So we have done the fitting for MOB distribution, then MOBW distribution, and MOBCH and MOBXI distribution. This is the empirical versus fitted plot, and we got these are the estimates, and these are the confidence interval, and for the p-values from the KS test, so that we can, for goodness of fit, we have done this for the minimum and marginals with the theoretical and empirical, and these are the p-values, and these are the AIC value and MML values. AIC value is to detect which is the best model, and based on that we can see that MOBW, MOBCH and Barth-Webb, they both are reasonably good fit. Though for Marshall-Walker bivariate exponential we cannot reject, but case test gives a poor result, and for TTT plot also indicates poor result. And for Marshall-Walker bivariate Barth-Webb, actually theoretically for this particular alpha we are getting, it shows a upside down hazard rate instead of increasing hazard rate, so we can reject that. So and Marshall-Walker bivariate chain distribution is giving the best fit in terms of MLL and AIC value. And so this can be used for enhanced reliability evaluation, also for preventive repair planning, inventory control, and for managing warranty cost, also for strategic reliability planning. And so for future research, we can see that we have used that constant shape parameter. It can be do for non-constant. We have taken FRM model instead of, we can go for cumulative exposure model. And we have used for marks data. We have not used any marks data, so sometimes observation marks is missing. So also you can use some maximum product of spacing or Bayesian framework for this. So
Well, your time is over. Very good.
Yeah.
Very good. Thank you, Dr. Sarat Sindhu Mukhopadhyay. Professor Ghosh. Professor Ghosh.
Dr. Sarat, it was very interesting talk, and I think it is very sweet talk, I can say. Now, my question one is that you have taken that 3 parameters C0, C1, and C2.
Yes.
It belongs to which variables?
No, this does not belong to any variables. Basically, this comes from the variable lambdas. So whenever we are considering the power law, whenever we are considering the power law, in the power law it is coming for the power law. So we are assuming that lambda ij is.
So is there any restriction on these values C0? That
They are positive. They are positive.
Okay.
They are positive here.
And that is one thing that for TT plot graph,
Yes.
your hazard rate was increasing.
Right.
So what you is it good sign?
No, actually it is, we cannot say from that it is good or bad, because generally whenever suppose stress level increases, the hazard rate automatically increases. We can say that. So based on that, the model is done, because whenever higher, we are going to suppose S1 to S2 and S1 is less than S2. So hazard rate should increase. So this is the scenario.
Okay, thank you.
Professor Banu? Professor Madam Banu?
Can you just justify the title of your talk? Inference based on a novel failure rate based.
Yes.
Why have
yes,
you
ma'am.
used the word novel failure?
Okay, ma'am. So basically, the hazard rate I am showing you. Yeah, this has not been used. Like it has been used, but it has not been used for bivariate setup, and it has not been used for like multiple SSLT setup. So it was used for only simple SSLT or multiple SSLT, but without the competing risk or without the dependent competing risk. I should say. So this is the main thing which is more tractable and easy to use. So because if you go for any other model, which I have not shown here, like CM, like cumulative exposure model or cumulative risk model, the CDF become much more complicated. Here, the CDF is very easy to see because if you take the survival reliability function, so remove the 1 minus part. So you see this is the multiplication of some survival function, and in most of
Is
the
it
cases,
because of the basic assumption of series system that you used?
No. Series system is for competing risk. This is the assumption
I
of.
think you have used series system, no? In your basic assumption. I think I saw that.
No, actually, this can be shown as a series system whenever there are two or multiple risks.
Yeah.
So we can see a series system because one in series system, what happened that one components fail, the system fails. So
Yeah.
here also we are in competing risk also as well. I mean, the first cause of failure happens, the system fails or the product fails. You can say like that.
Okay.
Well, thank you.
Yes, sir.
Thank you, Dr. Sarath Sindhu Mukhopadhyay. You have given a very nice mathematical details about your work. And you have not described the applications.
No, actually, the application is for this data set. I have not shown the data set.
You mentioned that you have used a data set. What is the data it is about, and how your work is suitable for that data?
Okay, so just a minute, I can show you the data.
Take
actually.
1 minute. 1 minute.
Yes. So I'm sharing another. Yeah. So here you can see that this is the data set I'm using. So there is temperature, there is failure time. So these are the failure times, and this is the delta 1, delta 2, like for which it has failed. We get only one time of the failure. So which component has failed at that time. So for defined temperature, so up to 1.221, we have taken the first stress level, and after 1.221, it is 1.271. We have gone for
what
the
kind of
second
stress
level.
was given?
So it was temperature for this
Temperature stress.
Yes.
Okay. Fine. Thank you.
Thank you, sir.
Thank you for all the speakers. Now you can close your screen, Sarath Sindhu Mukhopadhyay.
Yes.
Professor Ghosh and Madam Banu. Now, as per schedule, 7:10 there is a break, and we have 2 more speakers. I do not know whether Jiju Giliara is present. Jiju?
Did you have joined in the I think initial stage?
I do not know. Rahul Banerjee and Divya Dennis are the two other speakers. Shall we break for 15 minutes and join again?
You can continue one person and then after that take break.
Because we have only 2 speakers.
3 na?
No. Jiju, I do not find Jiju, the first speaker.
Okay, then take break.
So
We can
let's
have a
break
break
for
for 15 minutes.
15 minutes. 25.
7:25 as like yesterday.
Okay.
7:25.
Thank you.
7:30 is okay.
7:25
It's
or
nearing
7:30?
7:15.
That's 7:25.
No, sir. Now
But
it is
7:30 is
7:11.
okay.
7:20. Okay, right.
No, 7:30.
Why 7:20? Keep it 7:25. Yesterday we did 7:25.
No. I have a very aged father. I have to give him his food and then join. So I'll just join as early as possible.
No problem. You can join later on. 5 minutes later you join. What is it?
Okay. I'll try to join as early as possible.
Okay, right. Thank you.
7:25 started and joined.
Okay, okay.
you.